Boys and girls, get ready. Section 7 here is some pretty awesome but random two theorems. You're going to see the one right behind me. It really doesn't seem to fit with much, but it's a pretty cool thing. Look in your book, you'll see how it kind of flies, and you actually will need your book with a couple examples that I show you here, so get it out. But here is Theorem 110. I'm actually going to do Theorem 110 and then come back to Theorem 109. Whatever, bear with me, you know. Theorem 110, it says this: a median of a triangle, divides the triangle into two triangles with equal area. I didn't even know it was possible to get that many triangles in one sentence, but there we are. Now you look at this overall triangle DAC. What a wonderful triangle it is. What's cool about it over here in red, you see triangle bad, this one, is certainly not congruent to triangle BCD. There's no way they're the same size. They're not the same shape. They sure are triangles, but they're not even close to the same size. So they're not congruent. But what's really cool about this theorem, and look in your book, it shows you exactly how it comes about. It's awesome. It tells you that if you know the overall area, like of triangle DAC, D-A-C, is 54 inches squared, it means then, this theorem says, if that's the median right there, it divides into two triangles, where as you see, area of triangle bad would be 27 inches squared, and triangle DBC would be 27 inches squared. It doesn't matter what the triangle looks like, how big, how small, that median divides the triangle into two triangles, not congruent triangles. Two triangles of equal area. Is pretty cool. I know, random, but cool. Okay, let's do a little recap. Back to when we talked about this little thing right here. Woo! The old Spanish triangles. Just kidding. These similar triangles. Remember with similar triangles, two things were true. Corresponding angles were congruent, and the ratios of the corresponding sides were all equal. And remember when we had two triangles, this only dealt with triangles, not other shapes, just triangles. When we proved them congruent, we used the squiggy theorem. Similarity, we needed to prove two angles of one triangle congruent to two angles of another triangle. That meant the triangles were similar. It did not necessarily mean that they were congruent, but it did mean that they were similar. So we knew we had the same shape, but not necessarily the same size and shape. That's the deal. Don't forget, we also had these three too. We had the squiggy, SAS squiggy, and SSS squiggy. Although this is the one, of course, that we use the most. Why am I telling you that? Because in this next theorem, which is Theorem 109, Theorem 109 deals with similar figures. Notice it doesn't say similar triangles. It's any polygon. As long as they're similar, this theorem will apply. And it's pretty cool because it can be used to find areas or side lengths or all kinds of things. But here's what you need to write in your notes. If two figures, not triangles, any figure, are similar, so if you know that they're similar, or you can look at it and say, yes, they are, I know they are because of X, Y, and Z we just talked about, if it follows the rules. Then, the ratio, something over something, the ratio of their areas is equal to the square, meaning 2 square, of the ratio, something over something, of corresponding what we call segments. Now, what are segments? Well, in any particular shape, we have all kinds of different segments. We're not just talking like the sides. It could be sides, altitudes, radii, apophthegms, medians, diagonals, angle bisectors, and there's probably more, but that's the ones I can think of off the top of my head. Any of those are what we call segments, and if they're corresponding things, segments, then it will work and you can put it into this formula. Here's what it says. Again, back to the wording. If two figures are similar, then the ratio of their areas, area 1 to area 2, is equal to the square of the ratio of their corresponding segments. So ratio of their corresponding segments. This right here, formula, burn it into your mind because it's a really cool formula to be able to figure out certain things. And you'll see when we do some examples. Now what I'm going to do for you to show you how this works is I'm going to do number 1 in your book for you, A, B, C, and D. I'm going to show you number 2 in your book, A, B, C, and D, and show you the differences and what it's asking you for. So let me slide this across. Here's example number 1. 1A, 1B, 1C, and 1D. The question is to find the ratio of their areas. And you look in your book as I'm going through these examples. If you don't have it out yet, get it. But you're going to see a rectangle and a parallelogram in number 1. Well, all I have to do is to find the ratio of their areas. I must first find their areas. So, area of a rectangle is base times height. The first one's 90. Area of a parallelogram, the rectangle, or the parallelogram formula, is base times height. 9 times 10. So 90 and 90 are my two areas of the rectangle and parallelogram. But the question didn't ask you for the area, it asked you for the ratio of their areas. So, that means I'm going to put the rectangle to the parallelogram, which is 90 to 90, which is 1 to 1, or my answer is just 1 over 1. That was your answer. It's not telling you the area is 1, it says the ratio is 1 to 1. Nice. Number 1B. I almost said number B. Weird. 1, letter B. You have a triangle on the left and a triangle on the right. The formula is 1/2 base times height. Right there is your calculation for the first area. 20 units squared. Oh, did you catch it? I just realized I missed a unit squared up here. You're welcome. Keep going. The second triangle is 40 units squared. So the question is not the area, it's what's the ratio of the areas. So triangle 1 is 20, triangle 2 is 40. The ratio is 20 to 40, which reduces down to 1 to 2, or just plain old 1 over 2. Sweet. 1C, two triangles. Triangle on the left, calculating the area is 10 times 6 to half of that, 30 units squared. Triangle on the right, 1/2 base times height, 1/2 4 times 8, which gives you 16 units squared. Triangle on the left to triangle right. The areas, the ratio of their areas is 30 to 16. That would reduce by 2, which would be 15 to 8. And there's your answer, 15 to 8. So the ratio of their areas is 15 to 8. Again, it's not saying the area is 15. It's not saying the area is 8. It's just saying the ratio of their areas. Like, what's the ratio of guys to girls in class? It might be 1 to 2. It doesn't mean there's one guy and 2 girls in the class. It means the ratio is 1 to 2. That's a good example. Over here to the right, bottom right, 1D, two triangles. There's your area of the first one, 5 units squared. Oh, that's a cute little triangle. Over here, 2, 6 units squared. Oh, a cute little triangle. So the ratio of their areas is just 5 to 6. And that's it. Now, I want you to look at the directions in number 2. Number 2's direction says something about the figures in each A, B, C, and D being similar. That's a major different question than what you saw right here in number 1. Number 1 didn't say they were similar. Hence is why I didn't even use the similar figures theorem, Theorem 109. But in number 2, I have to, because there's no other way for me to figure out the ratio of their areas. So, depending on the question, maybe you can calculate the areas. Great. Do it and put them over each other. Or, if you can't, maybe there's similar shapes, figures, of which you can use that theorem. So let's do it. Here's number 2. So you have to use the similar figures theorem, which says the ratio of their areas is equal to the square of the ratio of the corresponding segments. Great. 2A, what it tells you is that there's the shapes, the side lengths is given to you to be a 5 and a 2. Sweet. Let's use it. So put the 5 and the 2 in for the side lengths right here, or the segments, I should say. So 5 and 2, and I square that. So when I square 5 and 2, it basically means I'm doing this. I'm taking 5 over 2 times 5 over 2. That's what squared means. And 5 times 5 is 25. 2 times 2 is 4. So there is my answer. Please understand this. It's not saying the area of the first shape is 25. It's not saying the area of the second shape is 4. It's just telling you that's the ratio of their areas. Majorly important. 2B, the side lengths are 6 and 9. Phenomenal. So you put 6 and 9 in here, and again, remember, the shapes are similar, so I can use this theorem. So I put 6 and 9 up there, and there's actually 2 ways to do this one. You could take 6 over 9 and square it right away and get 36 over 81 like this, and then reduce it by 9 and 9, which gives you 4/9. That's one option. The other option, kiddos, is to reduce this first by saying, wait, I can reduce this by a 2 and a 2. Oh, sorry, divide this by a 3 and divide this by 3. So that means then I have this fraction reduced down to 2/3. And when I square 2/3, whatever, When I square 2/3, I get 4/9. So I don't care which way you do it, but you do get the same answer. Okay? And you notice, over here now, in 2C, the altitudes in the triangles given to you. Nice! So their corresponding segments. Great, put them in here. 8/4. I reduce that 8/4 to 2/1. Square that, you get 4/1. That is the ratio of their areas. Again, it doesn't mean the area is 1 and the area is 4. It's just the ratio of their areas. So, last one, 2D. Side lengths are given to you to be 2 and 6. Great. And they're similar shapes. It told you in the directions that they're similar. I'm not making it up. They told you that. So, I can take them in there, or put them in the actual figures, similar figures theorem. Reduce this down to 1/3. Square that. 1 squared is 1. 3 squared is 9. And ladies and gentlemen, yes! We now have our ratio of the areas of those similar shapes. So we're going to practice these. You can do a lot more of these cool things with these theorems in many different examples to try to help you figure out different areas and different side lengths. But there's the basics. Let's practice it in class. Later!